Hello everyone. Welcome to the course Material Characterization by Professor S. Shankaran of IIT Madras. This is the live problem solving session for the week 3 of the course. I am Mayan Goyal and I am a research scholar in the Department of Electrical Engineering, IIT Bombay. So the course is being taught by Professor S. Shankaran, who is an associate professor in the Department of Metallurgical and Materials Engineering, IIT Madras. And the course plan for the third week is differential interference contrast, fluorescence microscopy, and sample preparation and applications of optical microscopes. So this live tutorial session is happening every Sunday 6 p.m. to 8 p.m. at this Google Meet. So as always, I will be showing you practice questions. But so last time I had a request from you people to do some theory on the topics first before going to questions. So, I've to explain the theory. I have prepared some slides. So these slides are AI generated. So don't take e- everything that is written on word to word. So let's start with DIC, which is differential interference contrast. So the main concept in DIC is that it is it is a type of phase contrast last week we studied about phase contrast microscopy. So DIC is kind of an improvement on phase contrast microscopy, so that you don't get halo effects that you get in phase contrast. Also, it utilizes full numerical aperture of the objective, so you get higher resolution, and it is effective in both transparent biological as well as opaque material samples. Phase contrast is generally used only for biological samples. So the core concept of DIC is that it transforms the local gradients in optical path length that can be due to refractive index or due to thickness, and it converts that into contrast, and as a result you get a monochromatic shadow cast image which has a pseudo 3D like appearance. You can see in this image, you can see the contrast between different layers. So the concept is that it is able to view it. So in phase contrast, the changes in optical the change in optical path length is used to give you the contrast. Here the gradient is used to give you the contrast. So you can see here, you can see here as you go from here to here and come back. So there's the op- optical path length changes. So in phase contrast, this difference in optical path length will result in the contrast, and the edges will result in a halo effect. But in DIC, the the derivative of the, this optical path length, the derivative of this is taken, and so you get as at the edges of the edges of your object, you will get a sharp increase and decrease. and this is what is read by the DIC, and it gives intensity according to that. So since it, it is giving the contrast based on where you are getting the halo effect in phase contrast, you don't get the halo effect here. And so it can also detect increase in path length and decrease in path length, and accordingly give you brighter and darker edges. So that creates a pseudo 3D like effect with shadows. So as you can see, positive and negative slows, bright and dark edges. So that creates the shadows and that gives you a pseudo 3D effect. So the key distinction between phase contrast and DIC is that phase contrast transfers phase differences into amplitude, whereas DIC transforms the derivative, that is gradient, of the optical path difference into amplitude. And the main component of the DIC system is the Nomarsky prism, so which is a modified version of the Wollaston prism. So Wollaston prism is a prism which which takes the polarized light and separates it into ordinary and extraordinary rays. So in the Nomarsky prism, there are two such Wollaston prisms attached in opposite direction, and the first prism first prism is used to separate out the optic ordinary and extraordinary rays, and the second prism is used to align them align the rays in a particular direction. Provide a shear between the rays which is very small, and the rays then pass through different, so the ordinary and extraordinary rays are now physically separated, so they pass through different adjacent points of the specimen, and when they recombine they give a contrast relief. So so two prisms are used, one before the objective and one before the specimen and one after the specimen. And so when when the second prism recombines the rays, it includes the information of the path difference as the rays traverse through the specimen. So this is how it will look like. So first you need to polarize the light. So so polarizer is used. Then you have a Nomarsky prism, and then you have your condenser. So the Nomarsky prism separates out the rays. Then it go through the specimen, and you can see through the specimen they they go through different gradients. And when the Nomarsky prism in the near the objective recombines the rays, the the phase contrast, the pathlet difference between different specimens are registered as a contrast, and then an analyzer is used which is at 90 degrees from the polarizer, so that it cuts off all the light except the except the contrast images light, and that gives you the the amplitude of the light. So you have two polarizers, one below, another above the objective and above the your prism, which is your analyzer, which and they are and they are in cross positions, so that they extinguish the background and only our specimen details are observed. And also there's one thing here is that the DIC prisms are different for different ob- NA. So if you are using higher NA objectives, the DIC prism will have a slightly different shape compared to lower NA or air objectives. One critical consideration is that you can't use plastics because plastics themselves are birefringent, so they will destroy the polarized light by dividing it further into different components. Next is fluorescence microscopy. So in fluorescence microscopy, you so you use the physical phenomena of where an object absorbs light, and that absorption of light is used to excite an electron from ground state to an excited state. Then there's an internal conversion inside the excited state, which brings the electron to the lowest excited state, and from there the electron goes back to the ground state while emitting a photon, which is called a fluorescence emission. And due to this internal energy loss, the emitted photon has a higher lower energy or higher wavelength than your absorbing incident light. So we can detect this output fluorescence output and use that to identify different regions of the specimen. So this difference between excited light wavelength and the emitted light wavelength is called your Stokes shift. And this shift is very important to for isolating the emitted signal from the excited signal. So how a fluorescence microscopy works is that, so this is in reflected epi illumination. Epi means reflected light illumination. So in a reflected illumination, your excitation light comes. So first you have an excitation filter which blocks which which is a band pass filter or a long pass filter which blocks all the light above a certain wavelength or only allows a certain wavelength of light to pass through. Then there's a dichroic mirror here. So the light hits this mirror and goes down to your specimen, and then from the specimen the incident light is reflected as well as your fluorescence light also comes back, and then it goes back to a dichroic mirror. So now this dichroic mirror has a special property that it allows only a certain wavelengths to pass through and reflects the other wavelengths. So let's say it will if the wavelength is below 500 nanometer, it will get reflected, and if the wavelength is above 500 nanometer, it will get transmitted. So why this dichroic mirror is important here is to block the excitation light from going to the eyepiece. So so this dichroic mirror edge is chosen that the edge of reflection and transmission is between your excitation and emission light. So only uh, only the fluorescent emission light will pass through, and then there's another filter here, another so this is a short pass filter or a band pass filter which will which will which adds as an additional barrier to block your excitation light and only allow your emission light to go through. So now so the only your emitted light will go to your eyepiece and you will be able to observe the only the regions which are fluorescent, and regions which are not fluorescent will appear dark. So this is so there are different ways you can do different ways of doing this fluorescence microscopy. The most common is the wide field where the complete sample is illuminated and the light from the whole region of interest is whole illumination region is reflected, but it is simpler, but it also includes regions which are out of focus and can give you blurry images. Then there's a confocal which only excites a very small point, which is so a pinhole is used so that only a very small region of interest is viewed, and this can then then your it and then your whole sample is scanned so that you can do different regions and you can also see which are in focus, which are not, and so you can modify your focal length to get. So this will allow you to get 3D information also. Then there can be multiple multi-photons which uses infrared photons for deeper penetration into your sample. Then you can also use total internal reflection, which uses only the surface level, which only works at the surface level. Now, in case of biology, cells are specifically stained with fluorophores to see very specific objects. Like for nucleic acid, you will use these type of fluorophores to get structural information. These type of fluorophores are used to see antibodies. Certain fluorophores are used to see genetic information. GFP type of fluorophores are used. Next, we will come to sample preparation. So the purpose here is to have a representative sample that we can observe under the microscope, but while making sure that we don't alter the structure of the specimen. So this section is very specific to metallurgy. It has nothing to do with biological sample preparation. So your first step will be cutting the sample to view the region. So cutting is generally done with abrasive wheels, abrasive coated wheels, along with coolant, which can be water or a soluble oil. So the coolant is used to keep the sample cool to prevent damage from heat. The rule of thumb is to use hard wheels for soft materials and soft wheels for hard materials. Then you want to mount your specimens onto your onto your certain mounts, and for that two types of methods are used: hot mounting or cold setting. So in hot mounting, phenolic resins or acrylic are used, and they are generally done at 150 degree at 15 to 30 Newton per mm square pressure. But for materials which are heat sensitive or do not have proper shapes, for that cold setting is used, which where we use epoxy, acrylic, polyester resins, and there then curing of these resins is done at room temperature. Then grinding and polishing of the surface is done, where you will first do grinding, which is grinding is done at different mesh sizes. So a lower mesh means uh, it will create coarse features on your surface, while a higher mesh means it will create finer features on your surface. So grinding is done for starting with lower mesh like 150 and slowly increasing to higher mesh like 800, which are generally silicon carbide papers. And also you will also use water cooling to prevent heat, and you also need to rotate your sample 90 degrees between every step, so that you remove the previous scratches. After that you do polishing to polishing to make your surface even clearer, and that is done by two methods: rough polish, which is done by alumina, and then fine polish, which is done by diamond paste. And and you have to constantly rotate your sam specimen with respect to your polishing, to prevent comet tails, which are like which which are very thin scratches, very fine scratches, which so to prevent that you have to keep rotating your sample during polishing. Next would be etching. So now you want to see the internal structure of a specimen. So for that you will do chemical etching to remove to see the internal structure. So what etching is done is it will preferentially attack grain boundaries, or it will preferentially stain the grains based on crystallographic orientations, and that will be that those can then be observed under the microscope. So there are methods like you can do deep etch, which will which will take longer time, and which are so they will they will create a higher relief, so they are good for lower magnification. But if you want to go to high magnification, you don't want to go very high relief, otherwise you will keep losing focus very immediately due to shallow depth of field. So shallow etch is done at shorter time. There are techniques that can be used, such as swabbing or immersion. Swabbing means you take your take a swab and your move it across your sample. So the loop is like first you etch, then you observe for changes. If it's fine, then you keep You stop and you clean out the agent by water, alcohol, dryness. If it's underaged, then you keep continuing. If it is overaged, then you have to repolish and then re-etch. If it's fine, then you can continue with your uh, observation. Uh, So these are certain agents for certain type of materials. So like for metals, for aluminiums, you use Keller's reagent like HF, HCl, HNO3. For iron steel, you use nitel, which is HNO3. For copper, you use ferric chloride. For stainless steel, you will use ferric chloride plus HCl. Then for plastics such as polyamide, you will use xylol at boiling temperature 70 degrees. For polypropylene, you use nitric acid and sulfuric acid mix, which is again at higher temperature. So now I will come back to practice questions. Crystals of different orientations are etched at different rates. This results in contrast change due to the ledges formed at grain boundaries, change in crystal orientation, elongation of grains, resolution change. So if you know the answer, you can speak or write in the chat.
A is the correct answer.
So that is correct. The correct answer to be A. Contrast change due to the ledges formed at grain boundaries. So since different orientations are getting etched at different rates, at the grain boundaries, you will see that there will be a dips or rise, and that will create a contrast change in your microscopy. What is the usual magnification of a microscope if the numerical aperture of objective lens is 0.9, 250 to 500, 50 to 100, 450 to 900, 300 to 700? So the answer to this will be C, 450 to 900. So if you so as you increase your numerical aperture, your depth of field will decrease, and if your depth of field decreases, you won't be able to uh, get a lot of regions in focus at the same time. So if you want to go higher and higher magnification. So so for very high numerical aperture like zero point 0.9, you want to have a very high magnification like 900. Next, the three main etching techniques employed in the specimen preparation for optical microscopy are swab, immersion, and electrolytic. Which among these is are done manually? 1 and 3, 2 and 3, 1 and 2, 1, 2 and 3. That would be correct. The correct answer would be 1 and 2. So swab or immersion are done manually. So electrolytic is not manual, it is a chemical process. It is an electrochemical process, so it it is done using specific instrumentation. In fluorescence microscopy, the dichroic mirror acts as a bandpass filter. True or false? So the correct answer would be false. So see, there are three types of filters. One is short pass filter, one is long pass filter, and one is band pass filter. So short pass filter is a filter which will allow shorter wavelengths to pass through, but not longer wavelengths. Long pass filter will allow longer wavelengths to pass through, but not short wavelengths. And the band pass filter allows a certain wavelengths to pass through, shorter wavelengths than that and longer wavelengths than that, or both are blocked. So dichroic mirror can act either as a short pass filter or a long pass filter. So it will reflect shorter wavelengths and it will transmit longer wavelengths. So that's how it will separate shorter and longer wavelengths. But it cannot act as a band pass filter, where it is allowing only a certain wavelengths and blocking both shorter and longer wavelengths. That is why we use specific bandpass filters at your before and after your dichroic mirror. In DIC microscopy, the relationship between amplitude and optical part difference is direct, indirect, integral, derivative. So the correct answer will be D, derivative. So we have already talked about this. So the derivative of the optical part difference gets converted into your amplitude of your microscope. An image is three-dimensional with apparent shadows and a relief-like appearance. What could be the possible technique we have used? Phase contrast microscopy, differential interference contrast microscopy, fluorescence microscopy, opaque microscopy. So the correct answer would be differential interface contrast microscopy. So we have so we know that in DIC we get a 3D like structure. In phase contrast we will get phase difference. We'll be able to observe phase differences, but it was but it will be a uniform image, so it won't have a 3D appearance. Whereas in fluorescence, we are only able to see fluorescence emitting lights. In opaque microscopy, we see edges of the our sample, but we are not able to distinguish between the high point and the low point. That is only possible in DIC. A sample is having optical anisotropy. Which type of microscopic technique can give maximum contrast? Polarized light microscopy, differential interface contrast microscopy, fluorescence microscopy, phase contrast microscopy. So the correct answer would be A, polarized light microscopy. So optical anisotropy means that the objects so that the sample behaves differently under different type of polarizations or based on ordinary ray, extraordinary ray. So we use polarized light microscopy to identify those anisotropies. For DIC and phase contrast, it only looks at optical path refractive index or optical path length differences. It doesn't look at optical anisotropies. Choose the correct option. Chemical etching is a method to generate contrast between microstructure features and specimen surfaces. Chemicals selectively dissolve areas of the specimen surface because of the differences in electrochemical potential by electrolytic action. Statement 1 is correct only, statement 2 is correct only, statement 1 and 2 both are correct, and statement 2 is a correct explanation of statement 1. Both are correct, but statement 2 is not correct explanation of statement 1. Yeah, that is correct. The answer would be C. So the statement 2 is the correct explanation of statement 1. Comet tail effect is noticed after which stage of specimen preparation? Grinding, cloth polishing, etching, mounting. The correct answer is B, cloth polishing. So when you do polishing using alumina and diamond paste, that time you get comet tail effect, which are very faint, thin scratches like if structure in your sample. Choose the correct option. Statement 1. Fluorescent light microscopy is useful for examining objects that emit fluorescent light. Statement 2. A certain wavelength of light emits from the sample when excited by light of higher wavelength than the object. Statement 1 is correct only. Statement 2 is correct only. Both are correct, but and 2 is correct explanation of 1. Both are correct, but 2 is not the correct explanation of 1. So the so correct answer would actually be A. So here it's written D, but it actually will be A. Statement 1 is correct only. So the object is reached an excited state when the wavelength of light coming from source is smaller than the wavelength of light emitted by the object. So the statement 2 says the excited light is higher wavelength, but excited light has to be lower wavelength than the emitted light. So statement 2 is incorrect. Why do we rotate the analyzer when examining the microstructure of polarized light? To statement 1 to get destructive interference, statement 2 when the difference between ordinary and extraordinary rays is not zero. Statement 1 is correct only. Statement 2 is correct only. Both are correct and statement 2 is correct explanation of statement 1. Both are correct and statement 2 is not the correct explanation of statement 1. So the correct answer would be C. So during polarized light we want to when the we want to get destructive interference when the so when ordinary and external rays are not zero, that time also we want to get destructive interference. For that we rotate the analyzer so that we can see the changes in our specimen. Which part of a specimen will be highlighted in the dark field illumination in an optical microscopy study if the specimen is a polycrystalline metal with a few ceramic particles? Grain boundary, ceramic particle, grain boundary only, ceramic particle only, or the grains. So the correct answer is A, grain boundary and ceramic particles. So in dark field illumination, you are able to see the edges of the particles. So basically areas which are not flat. So so the grain boundaries are not flat, therefore you are able to see grain boundaries, and the ceramic particles are also not flat, so we will be able to see the ceramic particles. Which of the statement is correct with respect to the polishing? We should not push the specimen too hard against the wheel. We should rotate the specimen against the rotation direction of the wheel. One is correct, two is correct, both are correct, and two is correct explanation of one. Both are correct, and two is not the correct explanation of one. So the correct answer would be D. So both statements are correct, but both have different reasons. So we should not push the sample too hard against the wheel, as excessive force will generate deformation, and it may generate plastic deformation of the top, in the top layer. So therefore we should not push the sample too hard against the wheel, and we should keep rotating the sample against the rotating direction of wheel to avoid the artifacts of the comet trail. So both are correct, but both have different reasons. So hence option statement 2 is not the correct explanation of statement 1. A figure inclined surface is shown below. Which imaging technique gives the maximum contrast? Bright field imaging, dark field imaging, opaque stop microscopy technique, fluorescent microscopy. So the correct answer would be C, optical stop microscopy technique. So in the optical stop microscopy or dark field microscopy, the the flat flat regions appear dark and the inclined regions appears bright, which gives us which gives us very high contrast. An object of height 3 centimeter is placed perpendicular to the principal axis of a convex lens of focal length 15 centimeter. Find the size of image if the object is at a distance of 12 centimeter from the lens. 12 centimeter, 10 centimeter, 15 centimeter, 20 centimeter. So the correct answer would be C, 15 centimeter. So you are given the object distance, which is 12 centimeter. Focal length you are given 15 centimeter. When using the formula, 1 minus v minus 1 by u by 1 by f, you can calculate 1 by v equals to 1 v equals to 60 centimeter, and then you can get the magnification as v by u equals to 5, and you can then use the formula m equals to h2 by h1 to get image height equals h2 equals to m into h1, which would be 5 into 3, 15 centimeters. How should the initial focusing of the microscope be done? With the coarse focus moving the lens towards the specimen, with the fine focus moving the lens towards the specimen, with the coarse focus moving the lens away from the specimen, with the fine focus moving the lens away from the specimen. That is it. The answer would be C, with the coarse focus moving the lens away from the specimen. So you should, when you start focusing, you should always start with moving the coarse focus away from the specimen, and then accordingly you will adjust other moving towards the specimen coarse fine focus. Once you get a good good enough focus, then you will use the finer focus again, first away from the specimen, then towards the specimen. So this is to make sure that the specimen and the lens do not come in contact. The specimen preparation is important at metallurgy because a poorly prepared specimen can damage the microscope. A poorly prepared specimen will distract from features on the specimen. Only a well prepared specimen will reflect light. A poorly prepared specimen will corrode, and the resulting image will be misleading. the correct answer is B. A poorly prepared specimen will distract from features on the specimen. So it's not necessary that a poorly prepared specimen will damage the microscope. So unless you are, so if you are careful during imaging, you can you can image a poor specimen also, and any specimen will reflect light. Light reflection has nothing to do with well preparation. That is a microscope property. And so you are not, so for microscope preparation, we are not doing anything to prevent corrosion. That is separate. So the main purpose of specimen preparation is to make sure that the features we are getting are the features we want to observe and not some random features. So that is why we want to properly prepare the sample. The red tint plate, also known as a full wind sensitive tint plate, increases the contrast in a polarized light microscope because our light are more sensitive to red light, so it is easier to see the light in dark areas when there is a red tint plate. The red tint plate only lets a small window of wavelengths through and so increases the birefringence, refringence. The red tint plate displaces the ordinary and the extraordinary beam by an extra wavelength, so that small difference in birefringence causes larger difference in color. The red tint plate increases the difference in birefringence in the materials that the different grain directions cause a greater difference in color than in just the polarized light. So the answer would be C. The red tint plate displaces the ordinary and the extraordinary beams by an extra wavelength. So that small differences in birefringence causes large differences in color. Contrast in reflected microscopy tends to be caused by variations in topography and differences in reflectivity of areas. only differences in reflectivity of areas, only topography, variances in thickness of the specimen. So the answer to this would be A, variances in topography and differences in reflectivity of areas. So, so we are talking about contrast here. So the contrast will not appear due to thickness of, and because it's a reflected microscopy, so the variations in thickness of sample will not give you any contrast. That will come from topography. So flat region and inclined region will have different contrast, and the reflectivity, how much certain areas reflect, how much amount is being reflected from different areas, that will give you the contrast. If a graticule is observed under the 10x lens of a microscope so that the diameter of the field of view is from 150 micron to 450 micron on the graticule, what is the width of one lamella when it takes 15 lamellas to fill the field of view when observed under the 50x lens? 2 nanometer, 2 micron, 4 nanometer, 4 micron. So the correct solution will be D 4 micron. So a graticule is basically a very small, small scale bar. So when under dryness microscope, you are seeing it go from 150 micron to 450 micron. So that is a gap of 300 micron. And when you go to 500 x lens, you are increasing your magnification by 5x. So your FOV will reduce by 5x. So it will become so it will now it will show only 60 micron of the graticule, and that 60 micron is divided into 15 lamella. So that width of one lamella would be 60 by 15, that is 4 microns. When the aperture stop is made smaller, which of the following is correct? The depth of field and contrast increases, resolution decreases, brightness increases. One only, both 1 and 2, both 2 and 3, all 1, 2 and 3. The correct answer would be B, both 1 and 2. So the contrast may increase slightly, but if you close it too far, then diffraction fringes will appear, which will lead to misleading pictures. And the depth of field also increases, but the resolution will decrease slightly because of that. And since the aperture slots being smaller will restrict the amount of light leaching specimen, the brightness will also decrease. So that is the compromise you have to give for increasing the depth of field and contrast. When increasing the magnification on the microscope, which of the following occurs? The depth of field increases, the resolution limit decreases, the visible area decreases, the contrast increases. the correct answer would be C. So, so when we increase the magnification, the visible area will decrease. So the resolution limit will depend on your numerical aperture of the objective. If that generally when you increase the magnification, either the numerical objective NA will remain the same or it will increase. And if, the depth of field will decrease if the magnification increases, and the contrast is also not affected. So the the one thing that will definitely happen is the visible area will decrease. An objective of height 2 centimeter is placed perpendicular to the principal axis of a convex lens of focal length 15 centimeter. Find the height of the image if the object is at a distance of 12 centimeter from the lens. 10 centimeter, 15 centimeter, 12 centimeter, 60 centimeter. So the answer is A. So this is the same question as before, except the object height here is 2 centimeters. So again, U 12 centimeter, F 15 centimeter. You will calculate V equals to 60 centimeter. That will give us magnification equals to 60 by 12, 5. And then image height would be 5 into 2, 10 centimeters. So the correct answer would be here 10 centimeters. Which part of a microscope is used to support the slide containing the specimen? Eyepiece, objective lens, condenser, stage. That is correct. The correct answer will be D, stage. So the stage is the part of the microscope where the slide containing specimen is kept. Eyepiece is used for observation. Objective lens is used for magnification, and the condenser is used to focus the light on the specimen. So that is all I had for today. Thank you for attending. If you have any doubts, you can ask now, or if you want, you can leave the video chat.